I was working on brain imaging in mice that are moving around, and there's this really difficult problem with that, in that you want to collect video rate data, but you want your implant to be very, very small. And that led us down like very thin endoscopy. The QuantIC side of this came into it because we were using SPADs, which are single photon avalanche detectors, which can detect very, very low light. They can count photons. So that's the marriage of those two, which brought me here, where I've kind of continued the work that I was doing with more functionality. We were trying to make a very thin endoscope, and you could imagine that a traditional endoscope comes in the form of these fiber bundles, where you have a series of fibers, they're very small and they're packed close together in a bundle, and each fiber acts as a single pixel. If you take that to its limit and you start making the fiber smaller, eventually at some point the photons will start tunneling through and your image will start to scramble. And in the very limit, you'll just have a single core, but the information's still there and it's encoded on the modes of the fiber. What we do is we take this single core multi-mode fiber and we undo the scrambling so that we can do imaging. And the way we do that is by using basically the guts of a projector, shining light on it and doing some phase shaping and sending light through the fiber to get a point at the end of the fiber, and then scanning that point across a seam with light to interrogate to pick up the light that's reflected back. QuantIC's sort of the bridge, bringing the solution to the people who might benefit from it. And there are applications for what I'm working on that I just hadn't thought of until QuantIC came along and found this connection. I didn't really expect the application of looking at nuclear cores, which was something that QuantIC had suggested, because all the electronics is done far from the site that you want to image. So if you're in a hazardous place, the only thing that has to survive it is the piece of glass that is your fiber. You're at a safe distance away and you're not compromising the structural integrity of your reactor housing because it's just a fiber. There are applications in security, or imagine that you want to defuse a bomb but you don't know what you're drilling into. Something that's the width of a hair is very useful. There is another application in medical endoscopy to do video-assisted surgery, one day leading to robotic surgery even. Obviously there's the application which I came from, which is brain imaging, where for research purposes we use mice, and the implant that you use has to be very, very small to minimize the hemorrhaging and the brain damage that you might get from putting in a very large implant. The potential is quite great, which I think is quite exciting to be a part of. I mean, I don't expect that I'm personally going to be responsible for medical imaging revolution, but you do steps maybe 7 and 8 of the 100-step process. I mean, it's fun sitting there solving puzzles, but it's also inspiring.